Electric field of multiple charges. Every charge creates an electric field around itself. The electric field is a vector. The electric field from each charge in a system will add as vectors at any location within the system, which will result in a net electric field at that point. Since it's a vector, the net electric field will both have magnitude and direction. So what you have is, let's say we have a bunch of charges here, and they all have electric fields, obviously radiating out in all angles. But at this point here, for example, this guy gives you an electric field there, this one an electric field there, this one like this, and you would add the three of them together as vectors, and let's say we add these three here, and we get a resultant vector something like that. Now that's terribly inaccurate, but just trying to give you the idea that we take the vector at this point due to each field and add them. Mapping the electric field at locations within a system of charges and connecting those lines results in the electric field configuration. Suppose we draw the electric field line below in black, and it's going like this. Okay. The direction of the electric field at any point is represented by the green arrows. It will always be tangent to the line itself. So here's an example of that. You can see how the green arrows are tangent at every point, and that tells you the electric field at that point. Let's say we had something like this, an electric field like that. Your electric field at this point would be there, at that point there, at this point here. So it is always tangent to the electric field lines. When we draw this, we don't have to have every space in the electric field configuration with an arrow. We'll assume that the spaces between the arrows still have a field at that location that can be estimated using the electric field on either side. In the example below, the electric field direction is shown for 2 points between this electric field line and this electric field line. We're kind of averaging these two curves, so here the electric field goes this way, and here you can see the electric field there would be like this, and here would be like this, so we kind of averaged the two. Again, these are just approximations and are just visualizations for us to look at. The electric field lines within a configuration also represent the lines of force on a positive test charge. Remember, because that's how we defined electric field, and here we'll use the vector format. It's the force on any charge that goes into the electric field due to your large charge. The tangent to that line, tangent to the electric field line, also represents the direction of the electric field force. To draw the electric field configuration, use the following rules. And again, this is just lines on a piece of paper representing the real physical condition of the space. The field lines will begin on a positive charge and end on a negative charge, or if there is no negative charge around, you just draw it like this. It goes out to infinity. That's what you're representing there. The density of the field line's distribution is proportional to the size of the charges. The greater the density, you would represent that by having more charges here, more electric field lines, and that means it's a stronger electric field and a larger charge. The lines never cross. Once you come up with an electric field configuration, you can't cross them. For example, let's say our electric field looks something like this. That's good because at every point there's a unique electric field which is tangent to those lines. But what if I had something like this? Draw some electric field lines here, and then this line here. That doesn't work because at this point and this point you have two different values for the electric field. That's impossible. It has one value after you add up all the vectors due to whatever many charges you have. So this is no good. Lines can't cross, and the lines are continuous. They can't do this. There can't be a break. The electric field exists at all points in space. This is the electric field configuration due to two like charges, positive and positive. There's no electric field midway between them. The individual electric field vectors cancel out. The shape of the field is the same for both positive and negative charges, only the field direction is different. Note how the arrows point in for the negative charge and away for the positive charge. If we have two unlike charges, positive and negative, or a negative and positive, once again the shape is the same. The direction of the field lines are different, right? Because they start on a positive and end on a negative. And there are no places where the electric field is zero.